Good day, my scholars. This is my school channel and my name is Abiola. For this video lesson, you'll be joining me to solve the JAMB CBT past question for the subject Physics, the year 2008. Do not go anywhere, stay with us and we'll be right back. Welcome back to my school YouTube channel. Right here, you'll be joining me to solve questions 26 to 49. So let's begin with question 26. In the microscope, the eyepiece lens merely acts as what? Alright, so this microscope, I think we should be referring to the compound microscope. Alright, so we have two converging lenses. We have the objective lens and this. Alright, so just like the name implies, the objective lens is that lens close to the object, then the eyepiece, the one for this. Okay, so what is the function of this eyepiece lens? We know that it's just acting as the magnifier. Okay, both lenses, the eyepiece and the objective lens, we know they have short focal length, but this has a larger one compared to the objective lens. So the function of this eyepiece lens is just to act as a magnifying glass for the object. So option D is the correct option. Short-sightedness can be corrected by what type of lens? So that should be concave lens or diverging lens. Every other option is there. Out of short-sightedness, that's myopia. The person cannot see distant objects. Okay, so and in such conditions, it's brought to focus in the front of the retina, not on the retina. Long-sightedness, and that's because it can be because the eyeball is actually too long, So the correct option is option A, concave lens or divergent lens. We don't have divergent lens here, so option A is the best option. A short chain is sometimes attached to the back of a petrol tanker to do what? All right, so in the transport of liquid contents, all right, like petrol or fuel, all right, as the petrol tanker, we're talking about a metallic body. As it moves through the air, there is friction, and that leads to the acquisition of electrostatic charges. All right, so the only thing that can be done, or the right thing to do, let me put it that way, is to actually conduct these excess static charges through that chain down to the earth, right, where they are neutralized. So the best expression here is that it's just to conduct excess charges to the earth. So option D is the right option. 29. An electric generator has EMF, electromotive force, of 240 volts and an internal resistance of 1 ohm. Okay, so if the current supplied by the generator is 20 amperes, okay, when the terminal voltage is 220 volts. So find the ratio of the power supplied to the power dissipated. Power supplied to power dissipated. So at first, we just recommend it. Let's start with the power supplied. So for power supplied, that's actually I times V, right? Formula for power, you can use I times V. So we have 20 amperes, right? You said if the current supplied by generator is 20 amperes, when the terminal voltage is 220. So that's actually 20 times 220, right? 0, we have 0 right here. 2 times 22, that is 44, right? Okay, so we have this already. Remember the unit of power, that is watts, right? Then we are now told that the power dissipated, right? Power dissipated, let me just save time. Power dissipated, that will now be the, we can use for power, we have different formulas, right? I can use I square R, or I can use IV, or I can use V square over R. So I think I will just go with this. All right, so right there was my V. Now look at this. An electric generator has EMF of 240 volts. That is the EMF right there. But we are not told that when the terminal voltage is 220, that means there's a drop, right? So that is 240, right, minus 220. And that difference is actually 20. Okay, so that means, since I'm using this formula, V squared over R, so that is 20 raised to power 2 over our R. What's our R? 1 ohm. So we have this, so that is 20 times 20 over 1, that is actually 400. So the ratio of power supplied to power dissipated will just be 440 ratio 400 watts. All right, that still means that 440 right over 400. Okay, 4 year 1, 4 year 11. That is 11 over 1, or you can say 11 ratio 1. So this should be our correct value. So 11 over 1 or 11 ratio 1. Let's go back to the screen. All right. So option A is the right solution. 30. A generator is on daily use, and in the process 10 60 watts and 5 40 watt tungsten bulbs are on for the same time interval. Okay, so the energy consumed daily is what? So daily consumption. So we can just take that energy, right, equals power. So considering the power first, we are talking about two different sets of bulbs, right? We have 60 watts bulb. How many of it do we have? We have 10 of it, isn't it? Then we also have another set of bulb, that's a 40 watt bulb. We actually have, how many there? Yeah, we have 5 of that. Okay, so that is 10 times this, that is 600 watts. 5 times this, that is 200 watts. So the power consumed altogether, that should be 800 watts. Okay, so that is energy equals 800, right, times the time, that is 24 hours for a day. They said daily use, that's 24 hours. So that's times 24. This should give me 192, right? Yes, 192, and I have 00. If I'm to bring this to kilowatts, right, the standard. Okay, I have 1, 2, 3, so it should be 19.2 kilowatts. So 19.2. Let's go back to the screen to confirm our solution. Yes, we have representation right here. So option B is the correct option. 31. The DC generator has essentially the same components as the AC generator except the presence of what? Okay, so AC generator, alternating current, right? DC generator, steady or direct current. All right, so of course we have carbon brushes in both generators, but for AC generator, the carbon brushes is touching the commutator. For DC, it is not. All right, but the basic difference that we can actually see is that in AC, what you have is a slim ring commutator. Then for the DC generator, we have the split ring commutator. So the difference now is that this generator has this has this. So the DC generator, the difference now is that the presence of split ring in this C generator. So option C is the correct option. Number 32. A step-down transformer has a power output of 50 watts and efficiency of 80%. Okay, so if the main supply voltage is 200 volts, calculate the primary current of the transformer. So remember the efficiency that we're referring to in this concept. Efficiency is actually power output, right? Power output, let me just put it here, and over power input times 100, isn't it? So we are from here. Okay, so we have our efficiency as 80, okay, equals power output is given as 50. So we are looking for the primary current. And remember that power equals IV, right? Current times voltage. So I is what we are looking for, primary current, times the V, which we are given as 200, okay, times 100 over 1. So year 1, year 2. So I have 2 year 1, I have 2 year 25. Okay, so by the time I cross multiply, I have IP times 80 equals 25. Okay, dividing both sides by 80, right? So the primary current should give me 0.3125 amperes. Yeah. Correct, primary correct. 0.3125. So let's go back to the screen together and see if we have that provision. We have 0.31. All right, this is the closest. So option A is the right option. Question number 33. All right, so we have cesium has a work function of 3 times 10 raised to power minus 19 joules, right? The maximum energy of liberated electrons when it is illuminated by light of frequency 6.7 times 10 raised to power 14 hours is what? So we are given the Planck's constant as this. So let's work together. Very easy. All right, so I will just have my solution. So we're asked to look for maximum energy. So I can use this, right? Equals HF minus the work function, right? So what's my H? Planck constant is given as 6.6, usually 6.62 times 10 raised to power minus 34. Then the frequency from the question is actually, I think, 6.7 times 10 raised to power 14. Then the work function that we are given, I think that is given as 3 times 10 raised to power minus 19. Okay, so when we multiply this, okay, just multiply the numbers first, okay, and then this should amount to somewhat around 44.354, thereabout, something like that. Okay, then times 10 raised to power, we have base 10, so that is minus 34 times changes to plus 14, and I have this as well. Okay, so minus 34 plus 14, that means you are owing 34 naira and you have 14 naira on you. So if you pay 14 out of 34 naira, what is left? That is 20 naira. So the 20 naira left is not your money, it's still a debt, so it's going to attract a negative sign. All right, so that should be 44, right, times 354 times 10 raised to power minus 20. All right, so I have to bring this to minus 19. So what can I do? I'm going to introduce it here. Okay, so instead of 44 points, so it's going to be 4.4. So let me just rewrite this. So it's just going to be 4.4, right, 354, right, minus, so this is 19 now. You can just use your calculator to solve all of this, all right, minus 3 times 10 raised to power minus 19. So don't worry about the raised to power. So just say 4.4, right, minus 3.0. So that should be 1.4. Then the 10 raised to power minus 19. So my answer should just be somewhat around that 1.4, yeah, 1.4 times 10 raised to power minus 19, something like that. All right, so let's go back to the screen to run a confirmation of our solution. Okay, I think we have something very close here, because I think this is presented as 6.6, right? But I use 6.2, so that is just a little variation. So we have 1.42 times 10 raised to power minus 19. So option A is the right option. 34. Zener diode is used for what? Okay, it's actually basically used for voltage regulation as well. Surge suppression as reference elements and other uses like that. Okay, so if you look at the working principle of the Zener diode, it's so much built in a way that once that threshold is being exceeded, it's going to allow the current to flow backwards. All right, so and we can call that the breakdown voltage, all right, or the Zener voltage. So basically it's just to regulate voltage. So the correct option is option C for voltage regulation. 35. When a pure semiconductor is heated, its resistance does what? All right, so semiconductor, you are looking at something between conductors and insulators, right? So for semiconductors, when you increase temperature, when it is heated, you are increasing temperature, right? The resistivity will reduce, right? The resistance property will reduce, while the conducting property will increase. I repeat, when you increase temperature of a semiconductor, this will go down, while conductive property will go up. So the correct option here should be option B is the correct option. 36. Which of the above are the uses of transistor? So we should just recall that transistor is a kind of semiconductor device, all right, that is used to amplify or switch electronic signals and electrical power, right? Okay, so and we know that transistor, it has many functions, okay, like detecting, rectifying, amplifying, switching, voltage stabilization, right, and signal modulating so on and so forth. So the correct options or the correct combination, like I mentioned, amplifying current, stabilizing voltage, power amplification, switching, and also as a switch, very, very important. So the combination should be all of this, okay, from what I perceive. So I have 1, 2, 3, 4. So I'll go for option A. So option A is the option we should be seeking for. 37. The dimension of electromotive force are what? Okay, so let's do this together. We have to move. So our solution, whiteboard. All right, so if you look at the definition of EMF, okay, so we can take it as this. Q, and we know that work done is actually force times distance, and Q equals IT, right? This is correct, this is time. Okay, so if let's just break this down, we know that force is actually mass times acceleration, right? And for mass, the dimension, you can still use m. Acceleration, if you look at the unit of acceleration, that is meter per second square, right? That is times, and meters, the length is measured in meters, right? Per second square, that is second, that is for time, right? That is over t squared. Or I can write this as L t to the power minus 2, isn't it? So this is for mass and this is the dimension for acceleration. So we've picked this apart. Then we still have another d here, that is for length, right? So this is L. So basically at the top we have this put together. Okay, so let me just settle this. M L t raised to the power minus 2 times L, right, over, we know that I, that is current. I can still use I, or I should use A, whichever one I want to use. All right, whichever one, maybe I or A. So let me just take with I. Then time, we know T is actually in seconds. Oh, okay, let's just use T. We're not using their unit per se, so let's just use, I can use capital T. I have capital T too, so let me use capital I as well. So those are their dimensions. So underneath I have I and then T. Okay, so if I break this down, I'm going to have L times L, that will be L squared. So I will have M L squared, right? I have a T under here, right? So that will make my T to be how many? Minus 3, because it's just saying something like this, T raised to power minus 2, right? Or you can say it's still something like this. T raised to power minus 2 actually means 1 over T squared. If you recall your indices, right, then we have times. This T is under 1 over T, isn't it? So that is 1 over T squared times T, that's T cubed, or T raised to power minus 3. Remember this minus 1. So this is why I have this. It's just an explanation. Okay, so we have this right here. Then we now look at the high that we have here. So I think the high should come in something. If I'm trying to arrange, it should come in before here. But let me just put it anyway. All right, so the high is actually raised to power minus 1 because it is underneath. So I should have ml squared t raised to power minus 3, then high raised to power minus 1. I prefer to put it here in terms of arrangements for alphabetical order. But let's just go back to the screen. All right, so we have ml squared, right, t raised to power minus 3, then this. So option A is the right option. 38. The resultant of two forces, 12 Newton and 5 Newton, is 13 Newton. So what is the angle between the two forces? Okay, this is very easy. So you can actually find out the angle because if you want to just do a regular addition of vectors, right, you will just realize that 12 plus 5 should give you 17 Newton, but right here you are having 13 Newton. So what led to this result? So we are going to find out. So if you are going to use this, the hypotenuse square equals opposite square, right, plus adjacent square. This is Pythagoras theorem, right? And we use Pythagoras theorem for right angle triangle. So right angle triangle tells you that 90 degrees is involved. So I've given you an answer even before, the answer before we worked out the steps. So we have hypotenuse square, which is the resultant that we are looking for, equals opposite. Let's take it as 12 square, then the adjacent 5 square. You can decide to bring this, whichever one works, okay? So I should have hypotenuse square, right, equals, this is 12 square is actually 144, 5 square, that's 25. So 144 plus 25, that is actually 169. So if I square root both sides to remove the square, so I have my hypotenuse as 13, you can see, Newton. So this works under the condition that at 90 degrees. Of course, the diagram to this particular solution is as well provided on the Myschool website. So for confirmation, the correct option is option C with 90 degrees. Don't forget that you can access any of the Myschool tools. All you just need to do is to first click on the link in the description below. This is going to travel you to the Myschool website. So right there you get to download the Myschool mobile app for your Android devices, or you can go for the Myschool software for your laptops and your computers. A force F required to keep a 5 kg mass moving around a circle of radius 3.5 meters at a speed of 7 meters per second. Okay, so what is the speed if the force is tripled? So this is a concept around centripetal force. Okay, and we have it like this, mv square over r, right? So I can use small r for radius. Okay, so I have my mass as 5, then the v, okay, it's given as 7, right? That's 7 times 7. Then the radius is actually 3.5. So I know 3.5 here 1, 3.5 here 2. 2 times 5, that is 10. 10 times 7, that is 70. All right, 70. So we have 70 right here. So we are not told that if the force is tripled, that means tripled means 3 times the force, right? And the force is actually 70. So that should account for 210. Isn't it 210? So if the force is tripled, we are now asked to find the speed. All right, so at first let's make V the subject of the formula. So given this formula, right, mv square over r, so that at first means fr equals mv square, isn't it? So if we divide both sides by m, so that implies that v square is equals to fr, right, over m. Okay, now this has been tripled. Don't worry, I'm going to remove the square. So that will be 210, right, times the radius. This is 3.5. 3.5 to me means 3.5, right? It still means 35 over 10, right? 2 here, yes, 5 here 2, 5 here 7. So it still means 7 over 2 to me, isn't it? So this is divided by m. Or I can say times 1 over, I say the same thing. What's my m? My mass is 5. Okay, so I know 5 times 2, 10. 10 is this is actually 21. 21 times 7, that is 147. So v square equals 147. So the square root of 147 should give me something around maybe 12.12 or 12.2. So my answer should be around this, 12.12 meter per second. That's the unit. So let's go back to the screen to run a confirmation. 12.1. So we have it here. So option C is the right option. Kindly send in your thumbs up by using the like button, and also do not forget the subscribe button, and always tap on this bell notification for you to get alerts immediately we upload the next video lesson. 40. A body of mass 4 kg resting on a smooth horizontal plane is simultaneously acted upon by 2 perpendicular forces, 6 Newton and 8 Newton. So calculate the acceleration of the motion. Okay, so at first we just have to recognize specific information supplied. All right, so at first we are told perpendicular forces, that is at 90 degrees, and that is referring to the use of Pythagoras theorem. So that is the hypotenuse square is actually the force, right? The resultant force, or I can say F, right, square equals the two forces, which are, I have 6 Newton and 8 Newton, so that is 6 square plus 8 square. That is actually F square equals, this is 36 plus 8 times 8, that is 64, and that should give me 100. So F square root of 100, that is 10 Newton. So we have to find the acceleration. Right here you should notice that we are looking at a smooth horizontal plane, so the friction there should be negligible, remember? So we have this, so right, so that means acceleration will be equals to force over mass. The force is 10, right? The mass is 4 kg, so that is 2.5. Right, acceleration, that's meter per second square. Okay, let's go back to the screen to run a confirmation. Yes, so the unit should be in square, so 2.5 meter per second. So option A is good to go. 41. The diagram above shows a plank RS, right, pivoted at its center of gravity O, and is in equilibrium with the weight P okay, and Q. So we have the weights P and Q. Now, if a weight 2P is added to P, so what's going to happen is that there's going to be a shift or a disturbance to the equilibrium, right? So you're going to see it's falling away. So the only way to prevent that is by, okay, so it's added to P. The Planck will be in equilibrium again by doing what? So if you look at this kind of scenario, right, this is point R, this is point S, this is O for equilibrium. So if I had extra weight here, you realize that it tends to fall off, right? So the only thing I can do to make the, right, to find the spot of equilibrium again is by altering the distance. So whose distance should change? Of course, both sides, but let's see a movement that we can do that can bring back this equilibrium. So if it's like this, because of the weight I've added here, the only way to counter that is to actually bring this, right, this is R, to bring it towards O. By the time I bring it towards O, okay, there is a kind of assistance right here. So you can try that at home, of course, or wherever you are. So once you have added weight to this point, right, you see it falling off, you have to bring this point close to the previous center O, right? You realize that as you bring it closer to try to stabilize or attain equilibrium. So the best experience that we can have here should be in option B, moving P nearer to O. This is going to counter the weight added. So option B is the right option. 42. The efficiency of the Pulley system shown above is 80%. Find the effort E required to lift the load of 1,200 newtons. So the VR of a Pulley system, you just count this circles that you can see. We have 1, 2, 3, 4. So the VR here is 4. So remember that efficiency is actually MA over VR. That is mechanical advantage over velocity ratio. Or you can say efficiency equals MA over VR times 100 over 1, provided that you have not used that percentage, right? That's 80 over 100 outside. I'm going to show you what I mean right now. So let's prove this. So efficiency is actually 80%, that is 80 over 100, equals the MA, we have to first solve for that. Then the velocity ratio, which is 4, 0 cancels 0. So I have this, 4 times 8 over 10 equals MA, right? So I think I can do something here. I have 4 times 8, that is 32. So I have 32 over 10 equals MA, and that is actually 3.2. Okay, so remember that MA, mechanical advantage, equals load over effort, right? So we are looking for effort. So what do we do? So effort equals load over MA, and the load we are given is actually 1,200 divided by 3.2. All right, so if you carry out this division, we should have 375. Okay, so that is the effort, 375. So let's go back to the screen to run a confirmation of our solution. Very well, so option C is the right option. Number 43, we have the diagram above is the eating curve for a solid. So QR is the what? Okay, so take note of this. You can see this curve is actually parallel, all right, to the time axis. So this tells you that the temperature here is actually steady, and that refers to the melting region. Okay, so the correct option is option A. That is the melting region. You can see temperature is actually steady right here. Temperature rises right here. So this is actually the melting region. So option A is the right option. 44. The above figure shows the motion of a progressive wave along a string. The particle motion of the medium is in direction what? Okay, so this is vibration of the particle, or you can say medium. Then we have direction of travel wave. Okay, this is for the wave, this is for the particle. All right, so this is your crest, this is your trough. Maximum upward, maximum downward. And this is a very good representation of transverse wave. Okay, so the correct option here is parallel to OY. So this is it. So option B is the right option. Question 45. If a concave lens of focal length 12 cm is used to produce a real image 4 times the size of the object. Okay, so how far from the lens must the object be placed? All right, so let's just start off with magnification. So we record that magnification is actually V over U, image height over object height, okay, or size over size, image size over object size. So the magnification produced is actually 4, right, over V over U. So we can see that V is actually 4U, isn't it? Okay, so let's go back to our formula, right? We're talking about a concave mirror. So we are told that from the question that it produces a real image. So that means that the solution I'm going to get, should be something around the concept whereby the object, right, will be greater than, I'm talking about the object value, will be greater than the focal length. All right, so just put that at the back of your mind. If not, what we should be producing will be a virtual kind of image. All right, and V is going to be negative. But right here, we'll be using a positive V. Everything is going to be positive. Okay, so we are looking for this. So that means 1 over F, the F is actually 12. So that is 1 over 12 equals 1 over U minus, we know that, oh, this is plus, please. Real image, right? So we have 1 over V. So V is actually 4U, isn't it? So that implies that I have 4U, or I can say 4U squared, whichever one I want to use. Okay, let me just use 4U squared. All right, so U in 4U squared, I have 4U. 4U times 1, I have 4U plus 4U in 4U squared, I have U. So U times 1, I have U. So basically, I have 1 over 12 equals 4U plus U. I have 5U over 4U squared. So U we cancel the square, so I'm left with 5 over 4U. By the time I cross multiply, I will have 4U times 1, that's actually 4U, equals 12 times 5, that is 60. 60 rather. So we can see that 15 is greater than. So this confirms the presentation that we have from the question, that this produces a real image because this is greater than this. This is for focal length, don't forget that. So let's go back to the screen to run a confirmation for our answer. So we have option B, so option B is the right option. Please do not hold back in asking those questions. All you just need to do is to use the link in the description below. This is going to get you to the Myschool website. Right there you get to ask your questions and interact with our solution providers. So what are you waiting for? So join me as I solve the next question. So I have find the effective resistance in the diagram above. So what you just need to do is just to find the sum of everything. We can do it right here. So this is of course an arrangement in series. Okay, so you can try to break it apart this way. This is a serial arrangement. This is that arrangement in series. So just add it up. All right. So 4 plus 4, that is 8 plus 4, 12 plus 4, 16 plus 4, 20 plus 4, 24. So the correct option is D, 424 ohms. You may have better steps or explanations or reviews you'd like to share. Please, we are so much interested. All you just need to do is to use the comment section below, indicate the question number and the explanations or points of views you'd like to share. 47. Given the inductor of inductance, we have 5, 10, and 20 connected in series. The effective inductance is actually the sum of all of this. So 5 plus 10, 15. 15 plus that is actually 35. And take note of this. Since we have an arrangement in series, okay, so the sum of all this, okay, will be greater than the largest value you can have here. So you can see the largest value we have here is 20. So the sum of the 3 or 4 or whatever amount you have there will be greater than the biggest of these values. Okay, so the answer here is 35. Okay, so where do we have 35? Okay, not 3.5, 35. So option D is the right option. 48. If electrons are accelerated from rest through a potential difference of 10 keV, okay, so what is the wavelength of the associated electron? Okay, so let's run a confirmation. So you can see this is actually 10 raised to power minus 31. This is 10 raised to power minus 19, and this is 10 raised to power minus 34. So this is for the mass, this is for charge. All right, so you can see the units, coulombs, and this is Planck's constant. So we can see that the relationship between work done, right, and the kinetic energy right here. So we know that kinetic energy is actually half mv squared, isn't it? And we can see that the work done is equals to this. So work done in terms of electricity, that's actually QV or VQ, whatever thing you want to use. So since these two are equal, so I can say QV, right, equals half mv squared. So let's determine this first. Okay, so that's going to be 2QV, right, equals half MV. Sorry, equals MV squared, the half. Okay, so what do? I divide both sides by M. Okay, so I have V squared equals 2QV, right, over M. Okay, so I square root both sides to remove the square. So I have V equals this. V equals 2QV, right, over M. All right, so that will be square root of 2, right, times the Q, which is giving us 1.6 times 10 raised to the power minus 19. Okay, times this, you know, it's, we have 10 kilovolts, so that is 10,000, right? The kilo is 10 raised to the power 3, so that's 10,000. Okay, that is 10, 2, 3, 4. Over, then we have the mass. The mass is giving us, yes, 9.1 times 10 raised to the power. Okay, so what you can just do using your calculator is you can punch this out, or you can just say 2 times 16, that is 3.2. So what I should be having now will be something like this, 3.2, right, over 9.1 rather, right, times 10 raised to power. This is 10,000, right? It's still 10 raised to power 4. So that is 10 raised to power minus 19, isn't it? Okay, plus 4. Then remember we have a 10 here. So this all over means divide, and that is minus. So minus, remember we have minus sign, minus 31. Okay. So minus times minus, this means plus. So I'm going to write this as plus 31. Okay, so we have 31 plus 4, that is actually 35. So 35 minus 19, not 9, that should give me 16. So I will have this 3.2 over 9.1, right, times 10 raised to power 16. Okay, so if I look at this, basically this is somewhat close to around 3 over 9, thereabouts. So if you carry out this calculation, or you can just punch your calculator from here, I'm just trying to break this down. Okay, you should have something around 5.9 times 10 raised to power 7, right, something around this. Initially you get 0.5 because of this, 0.59 whatever, or 58 thereabout. So if I'm going to bring it to this, so I'm going to half this. So just take note of this. You can play back this video again. This is our V. So recall that the Planck's constant, right, and the relation between Planck's constant, V, and mass can be gotten using the de Broglie wavelength. Okay, this is what I mean, de Broglie. All right, if you pronounce it that way, wavelength. I'm just trying to pin out this relationship, so we have it this way, equals H over mv. So this H is our Planck constant. And what do we have that as? We have that as 6.6 times 10 raised to power minus 34. Then what's our mass again? I think our mass is somewhat around, 9.1 times 10 raised to power minus 31. 9.1 times 10 raised to power minus 31. All right, then our V, which is 5.9 times 10 raised to power 7. Okay, so you can just punch your calculator for this. You should have something around maybe 1.21 or 223 thereabout. So basically I can bring this to 1.2 times 10 raised to power, yes, minus 11. Of course, when you divide this, okay, you will not have 1 point. What you are going to have is 0.12. So for me to remove that 0 and bring this to expression of standard form, so when I move that 0, then that's what affects the power here. So what you should arrive at should be around this 1.2 times 10 raised to power minus 11. You know, this I can't really break it down because it's going to require lots of calculations and the use of calculator. So just follow this step. All right, so let's go back to the screen to run a confirmation of this solution. Okay, so we have this. So option A is the correct option. Of course, you can use the other step to solve it, and I've actually done that on the Myschool website, so you can run a check as well. So option A is the right option. 49. In the equation above, the particle X is what? Okay, so you can say helium particle, so you are definitely talking about alpha radiation. All right, so as it bombards This is for nitrogen, right? Then if you look at this, if we add up what we have here, it should also give us the same value. So from here we have 18. You can see this is 9. So of course that is one is missing, right? So that is for hydrogen. And we can also refer to this as proton, because in hydrogen atom you just have proton and electron, no neutron. So this is definitely hydrogen, or I can say proton. So option A is the right option. So we've come to the end of this video lesson, but you know that there are more wonderful segments to come. All you just need to do is to always hit that like button for us, and do not forget the subscribe button, and always tap on bell notification for you to get informed immediately we upload the next video content just for you.